Welcome to our lecture. Today, we are going to finish chapter 9 and see how far we will go with chapter 10. We will start chapter uh, 10 today and see how far we can go with chapter 10. Please continue working on the homework assignment. Tentatively, the exam, final comprehensive exam scheduled for next week uh, will cover chapter 1 up to chapter 10, wherever we will get done with it. I would like to share information regarding the final exam scheduled for next week, not later than weekend. Usually, I love, giving you or giving my student 1 week to prepare for the exam. I'll try as much as I can today to cover what I believe you will need in Cam 2, both the lecture and the lab. You are required to take Cam 2 lecture as well as the lab. So today, before we get started, I would like to share the uh, statistics for last exam, midterm exam 3. There was 1 point improvement from midterm exam number number 2. This is um, this is the statistics where we are. You know where you are with the class. The average score was 88 percent. I believe midterm exam number 2 was 87, and I think exam number 1 was 89. Everybody or majority of the class, we are or they are right here. The highest score was 100%, lowest was 57. Please uh, work hard. As far as the final and the two more quizzes, quiz number 9 and quiz number 10, which I'll share more information as we go along. Now, having said that, let me just pull chapter 9 PowerPoint slide, and I believe we went as far as section 9.4. 9.4. Prior to this, we learn how to predict molecular geometry of molecules using the Fallon-Shell electron pair repulsion or model. There is, we use the Fallon-Shell electron repair model to indicate the shape of the molecule. So if you are given a molecule and you are asked to predict a molecular geometry, start off with drawing the Lewis structure, follow the guideline we looked at last time in terms of, the um, steps in, all right, steps in drawing the Lewis structure. You need to be able to, all right?
I think we only got to slide 15 last class.
Last slide 15, let me see,
Yeah.
slide 15, let's see, 15, where was it? Slide 15, let me see, if 15, it is a continuation of basically, let's say, right here. 15 is right here, learning the molecular geometry. All right. So at the outset, there are 6 molecular geometries you need to be able to understand, commit to your memory so that when you are given all of them, even though we learn maybe 2 or 3, Still, we use the same approach in determining the molecular geometry, which is this equation or general formula APX. You know, if you were here last time, you you know what this means. Stand for the number of EX stand for the number of moles. I mean the number of lone pairs on the on the central. Generally, A stand for the central atom. These are the external atoms, and these are the lone pairs of what? Lone pairs of electrons. So that when you are asked to draw the Lewis structure, you start off with, you look at slide number 15 here, all right? The molecule in question is sulfur. I think we did this sulfur trifluoride. In the Lewis structure, we do what? We find the total number of valence electrons. Sulfur is in group 6, all right? Fluorine is in group 7. 7 times 2, we have 14. So we have a total of what? A total of 20 valence 20 valence electron for sulfur trifluoride. With that, we draw the skeleton, the central atom, being the less electronegative, bonded to 2 fluorines. And remember from the Lewis structure, what do? We subtract the bonding electron from the total valence electron. So we have used 4 electrons here, subtract 4, remain 16, remain 16. First priority goes to external atoms in drawing the Lewis or in fulfilling the octet rule. So I'm just giving the external atom first priority to do it, to satisfy the octet rule, except hydrogen, external. So here we have used 12, 6 on each fluorine, remain 4, remain 4. Those remaining electrons, just put it on the central atom. You know, it doesn't really matter where you can put it at the top, but when you cut to the molecular geometry, you'll see how it look like. This is the Lewis structure, doesn't tell us, you know, the molecular shape. So what we need to do is zero in on the central atom, that our central atom is sulfur. And we have to focus on the bonding electron or the atoms and the non-bonding electron. This is of this type A with the central atom, B2, that means 2 atoms connected to the central atom, and E4, E4. So with that, you will look at I'll allow you to use this table, valential electron pair repulsion model. You're gonna use this in the quiz as well as the exam and see which one is, all right, which one is the general. Using the last column here, I use, I had to rewrite this. This is what we have here. Sometimes they are not visible, they are not legible, but you'll see this is the, this is E4, AP2, AP2, E, AP2, E4. 1, 2, 3, 4, 5. So we use 4, AP2, 4. So the molecular geometry is 6. So if we have 6, all right, if we have 6 electron domain geometry, if we have 6 electron domain geometry, we will have 2 lone pairs of electron P4, AP2, P4, AP2, P4. We have 3 pairs, 4 pairs. So we are use 4, 16, 12, remain 4, AP2, 2. This is 2 right here, not 4 pairs, it's 2. So it is this AP2, all right, where I'm getting this configuration. You see, this is the 2 lone pairs, and the molecular geometry is pen shape or V shape. If I minimize this and show you the from my whiteboard, this is the whiteboard. From the whiteboard here, AP2, because there are 2 lone pairs. This means 2 lone pairs of electron. And the type of the molecular geometry here is pen shape. This is the pen shape, which is the correct answer for slide number 15, learning check, learning check. Now, you had question about, slide 15, and I was almost starting 4. You do the same thing for tetrahedral all the way to octahedral. The point here is, are you able to interpret this formula on the whiteboard? Remember, this stands for external what? External atoms. And these are lone pairs. Remember, on the central what? Central atom. So for tetrahedral electron domain, this is not molecular geometry, electron domain, if it has three sides. So how are you going to look at that? If you look at this, for trigonal for 3-side tetrahedral, and then trigonal pyramidal AP3E1, okay? We have more geometries based on the lone pair, all the way to what? All the way to AP6 total for electron domain geometry compared to the rest. So for this, these are the 4 domains which you can use to either describe the electron domain geometry, which includes the lone pairs. But for molecular geometry, we only look at the atoms bonded to the central. This has 3 atoms and the lone pair setting up. So all of them, they have 4 domains, 4 domains. So the point is, you should be able to reconcile what I do have in the PowerPoint slide, what is in the text, with these general or summary or valence shell electron pair repulsion models. So you can have 2, all right, you can have 2 atoms bonded to the central. You may think that always when you have 3 atoms, all right, and then you think that it will be linear, just the way we look in linear. We have 2 atoms bonded to the central. Likewise for this tetrahedral domain, electron domain geometry, we can also have 2 atoms bonded to the central. So I will play by the guidelines, the rules for drawing the Lewis structure, which we learned previously, and see how many lone pairs of electrons are in the central atom before you make a conclusion on which, how the question is structured. Because sometimes a question could be on molecular geometry or could be on the electron domain geometry. These describe electron domain geometry, tetrahedral. And in electron domain geometry, you can have molecular geometry of tetrahedral, you can have molecular geometry of trigonal, pyramidal, you can have a molecular geometry of pen shape. And all of them, they do have. This means 4. And if I look at this, if you add, all right, if you add the lone pairs plus the atoms, it gives you 5 regions. It gives you 5 regions, give you 5 regions. For octahedral, 6 region, all of them will give you 6 region. All right. This, you need to know how to, for this particular one, let me just minimize this, see how you will approach the problem on the PowerPoint slides. So if you look at the molecule here, silicon is at the center, doesn't really matter, you know, the where you place the chlorines or hydrogen, all right, chlorine, chlorine, hydrogen, hydrogen. Let's see, just the way we did, you have to account for the total number of valence electron. Otherwise, you may miss the lone pairs which affect the molecular shape. So silicon is in group what? This is 4, all right? Silicon is in group 4. It asks for valence electron. And then what we need to do is add for what? 2 chlorines. 2 chlorines, which is 7 times 2 is equals to 14. And 2 hydrogens. 2 times 1 equals to 2. So we have 20 valence electrons, 20 valence electron. Let's subtract the bonding. We have used bonding here, so you know, just subtract 4, remain 16, remain 16. Hydrogen does not need 6 more, it does not satisfy the octet rule, that's the exception. So the only 2 atoms which needs to satisfy the octet rule are chlorine. So we're not gonna use 2 minus 12 remain. We are use silicon. Silicon is it group 4? Silicon is in group 4A, so it has 4. We have used 12 out of the remaining 16. How many remain? 4, right? So the 4 electrons we put there, and silicon is in group 2. Now, this is AP4E2, AP4E2. There are 2 lone pairs on the central atom. At this point, you should be able to tag all these molecular geometries. Remember, molecular geometry is different from electron domain geometry. Electron domain geometry 4 plus 2 is 6. So that is octahedral. With this, AP4E2, this is the shape. And if I look at the 2 definition here, it is octahedral. This is the electron domain geometry for 6 sides, octahedral and octahedral, and a molecular geometry is square octahedral for AP24, which means the geometry we have based on that 6 domains for 6 domains octahedral. You know, for the ions with an overall charge of positive, all right, with an overall charge of positive, we do what? We subtract. So this is a hydronium ion. Minimize this so that you see my whiteboard. For hydronium ion, H3 positive, H3 positive, the total number of valence electron, 3 hydrogens, this is 3 times 1 is 3. Oxygen is in group 6 times 1. This is 6, so total of what? Total of 9. The overall charge of positive means we need to subtract 1. Subtract 1. We have 8. We have 8 valence electrons. 8 valence electrons. So what we'll do is 8 valence electron. This is 8 valence electron. This will give us the molecular shape H bonded to that. We have used what? We have used 6, remain 2. We have used 6 electrons, remain 2. We put it on oxygen because hydrogen does not need more than 2 electrons. If I look at the central atom, the general formula is A for oxygen, P3, and then E1. This is a total of 4 domains. There is one domain here, one domain, one domain, one domain. So this is tetrahedral, but the molecular, you see this molecular, if I see AP3E, 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 all right, we look at AP3E. Which means central atom oxygen, 3 hydrogens, and the lone pair of electron. Tetrahedral, molecular geometry, and trigonal planar. All right, trigonal power pyramidal.
Where you subtracted 6?
Why did I subtract 6, right?
Yes.
Okay, let me go back here and then I'll show you why did I subtract 6 is because in Lewis structure, we subtract the bonding electron rule number 2 from the total. Remember the total we had 8. I am subtracting 6 because I've used 2 here, I've used 2 here, I've used 2 here from the total. So 2, 2, 2 gives me a total of 6 electrons used in bonding. These are bonding electrons. That is where the 6 is coming from.
Okay, so why did you subtract the 1 to begin with from the 9?
Yeah, the 1 is from the overall charge. This is the overall charge.
Oh.
Yeah, it was hydronium ion. You see this? So you subtract, if you have, let's say, NH4 positive, this is one of the 2 common polyatomic cation. This is a polyatomic cation. You subtract when it is an overall charge of positive. Compared to when you have an overall charge of -2, you add 2. If you have an overall charge of positive, I mean -3, you add 3 extra electrons. Does it make sense?
Yes, sir. Thank you.
Yes, there was an overall charge here. That is why I know it's kind of like, why are you subtracting it twice, yet usually we subtract 1 time because of the overall charge we had for positive. So here it is trigonal power pyramidal, and be careful because some question, all right, some question could be on electron domain geometry. If it was electron domain geometry, then I will go with the tetrahedral. But since it's molecular geometry, we'll go with the trigonal power pyramidal. So be careful on how you read the question. I don't want you to make a conclusion that if the same question, similar to what you see here, and then I change these to electron domain geometry, say I thought it was trigonal. No, it has to be specific, whether it is electron domain or molecular geometry. This is just, explanation of the how we end up with the bonds. Why do we say this, 104 or 107 or other angles than what we project from, the Lewis structure. For example, methane, it is oversimplified when we have for CH4, I'm just giving an example here of CH4, that sometimes you may have seen me or anybody else giving you the structural formula for CH4 methane ester, which it portrays a molecular shape with the point angle of 90 degrees. That is not, in reality, it is less than that. You see, it is 109.5. It's because of the effect of bonding or effect of electron. They tend to repel. They tend to repel. I wouldn't really, require you at this time to memorize the angles. I know in the table, apart from also being given the molecular shapes, bond angles also are given for each shape, which I don't want us to go in details into that. Now, I want to, this is just continuation of the molecular. This is second to last, trigonal power pyramidal, which if I use APX, all right, if I use APX, you will see that we have 1, 2, 3, 4, all right, 5 domains, trigonal power pyramidal. What I want you to learn is or understand is when we say equatorial versus the axial is on the opposite side of the central atom, perpendicular, but this is assumed that in 3D along the equator. You know, when we say equator, around this globe, it just go round, but assuming this is not pole, this is south pole, this is axial. For trigonal power pyramidal, sometimes you have lone pairs. Usually the lone pairs occupy the equatorial position, lone pairs. So if we draw the Lewis structure and at the end for 5 domain geometry, 1, 2, 3, 4, 5, the lone pairs occupy the equatorial position before placing on the actual position. Here are the terms used in describing the molecular geometries for 5 domains. These are the molecular geometries, trigonal power pyramidal, seesaw, T-shape, which it is given in the text how they look like, all right? Maybe if I blew this, you will see how the shape look like. Let me just blow this. If you look at the 5 domains, 1, 2, 3, 4, the equatorial, you see where they are compared to axial lone pairs. The purple loops here stand for the lone pairs. This will play out. I know you may think, and I pointed out earlier on that you may have two, all right, you may have 2 atoms hooked up to the central and you will think that it is always linear. No. Using this as an example, all right, let me use this as an example how we end up with the 5 domains. I'm just gonna minimize this so that I use my whiteboard. So if I have xenon, for example, xenon difluoride, xenon, like that, you may think that this is linear because we had previously linear, an example of a linear with 2 atoms hooked up to the central, but you have to draw the Lewis structure, follow the guideline. That is when you will see the lone pairs of electrons. So if we do that, our xenon is in group 8, so we have 8 valence electron. Fluorine is in group 7, so 7 times 2, this is 14. So if we add 14, this will be 20, 22 valence electrons. 22 valence electron. It's hooked up to what? It's hooked up to the central atom like that. And we want to satisfy the octet rule, so I'm just going to subtract 4 here. remain 18. I've used two on each side. This needs 6 more. This needs 6 more. I've used 12 here. Remain 6. Remember, we pair electrons, so I'm just gonna have this. I'm just gonna have that. I'm just gonna have that to make 6. Remember, we keep the central atom the last. Don't worry about like why is this more than more than 8 on the central atom. It has an expanded D sublevel. We can take up to 10 electrons. So this is of type. If I zero in on xenon, xenon is our central atom. B, we have 2 fluorines and 3 pairs. So if I add 2 plus 3 is 5, which means 5 electron domain. 2 plus 3, 5 electron domain. The blue loops you see here stand for the lone pairs, which occupies the equatorial position, and the lone pairs has that. So if I am to describe the electron domain geometry, it is trigonal power pyramidal, but the molecular geometry is linear. So you have to tag this as well. That how do you describe the electron domain geometry compared to molecular geometry? All because they are adding to 5. Electron domain geometry is trigonal power pyramidal, but molecular geometry can be trigonal power pyramidal. It can be seesaw. It can be T-shaped. It can be linear. It can be linear. Last now on that is the octahedral. All right, you can do that on your own. See how that plays around. This is just an example of trigonal power pyramidal. Last here is the electron domain geometry with 6 sides. Octahedral for 6 sides, and the domain molecular geometry can be octahedral, can be square based on where the lone pairs are, square planar based on where the lone pair are. So it's going to square planar for X or right octahedral in explaining the last 6. So there are 6 electron domain geometry you need to remember. If I were you, I'll summarize and be able to use that table. I'll allow you use this in the exam. This table you'll have to print out. Even for the quiz, you'll have to use these in order to come up with either electron domain geometry or molecular geometry. All right. Any question on molecular geometries? This is, I will not delve into linear molecules. Linear molecules means you have more than one central atom. They take one atom at the same time. I don't want you to look at that. We'll just leave that alone. Now, as far as the polarity, molecular polarity is concerned, this molecular polarity plays a role in physical as well as chemical properties of molecules are concerned. You have had like dissolve like. If you haven't, you'll come across that, which means polar molecules dissolve non-polar. Polar molecules dissolve polar molecule, or in other words, polar solvent will dissolve either ionic compound or polar molecules. Non-polar will dissolve non-polar. If you do not understand how you come up or to look at a molecule and say it is polar or non-polar, then it will be difficult. Now, water is a common universal solvent, and from what we have looked at so far, this is the molecular shape of a water molecule. the lone pairs of electron, to assume that shape, because of electron repulsion. Electronegativity plays a role. The electrons are being pulled towards oxygen, it's more electronegative, and we indicate this as partial positive, partial negative, partial positive electron pull. You see this delta positive, delta negative. Overall, we use this, that is the net displacement of electron, and we say that the molecule is polar. Based on the shape and how the electrons are displaced. Electron is displaced. You can have a simple molecule such as hydrofluoride, if I have that, or hydrochloric. This is partially positive, partially negative, because it's more electronegative, and the electronegativity indicate that is positive, molecule is polar. As opposed to now, say bromine, bromine. This is non-polar. So I'll use electronegativity to electronegativity as well as the molecular shape to see how the electrons are displaced before you make a conclusion on whether it is polar or non-polar. Sometimes we use electron potential map, where blue indicates the region with electron poor region, red electron rich portion of the molecule. This is non-polar because of equal sharing. This is polar because of unequal sharing. Forget about the numbers here on electronegativity values. You can use the trend on the periodic table. One thing you need to pay attention is presence of polar bond does not mean that the molecule is polar. This is non-polar even though we have polar bonds. Oxygen is more electronegative. It is pulling electron on this side for carbon dioxide. Oxygen is pulling electron on the other side, and the net charge will cancel out. Even though we have polar bonds, overall, the molecule is non-polar because of the net cancellation. We can have a molecule such as CH4, all right? There is an overall net charge or net cancellation, just the way we looked at that, and it will not affect that. So point here is for non-polar, polar. Any question on molecular geometry before we look at the bonding theories?
So we don't really need to worry about like the whole dipole like moments with the numbers per se.
No. Yeah, don't worry about
the trends. Okay. Okay, great.
Now let's look at the molecular bonding. In Lewis structure, we did not really, explain how the bond is formed or how electron participate in forming the bond. How is the bond formed? We have just been drawing, listen, we have just been drawing that, a dash means a chemical bond, right? We have two bonding theories, all right? Bonding theories. And you know what that theory is, right? To explain the reality of theory. There is the valence bond theory, VPT, that you see on the screen, and there is the molecular orbital theory. Molecular orbital, this is abbreviation for valence bond theory, how the bond is formed. And in this case, we are focusing on the covalent bond. Valence, from the word valence, you know what a valence is. Valence is the outermost shell, okay, and the electron occupying those those electrons in the valence shell are valence electron. And in this case, in valence bond theory, it proposed that a bond is formed due to overlap, such as in hydrogen gas, when hydrogen atom approach hydrogen atom, eventually there is an overlap. And the overlap where you see here, for example, the shaded, maybe I'll just have to blow this up so that you see the, not the light blue, but where there is an overlap. This is where now the bonding will take place, or the shared electron. I can have this to or demonstrate that how the bonding and how electron. From what we learned earlier on, if this is the electron from the second hydrogen and electron from the first hydrogen. I'm using here H as an example, H2, which is the same as H connected to that, but we didn't talk about how the bond is formed. From the valence shell, valence bond theory, it proposed that the sharing of electron is formed as a result of overlap of orbitals, and the shared electrons will occupy the space between the two atoms. Now, where the valence term comes here is, if you look at the hydrogen, this is 1s. For chlorine, the valence shell is 3p, and those shared electrons you see here 3p, and from the illustration here, the bonding has to do with the what? With the share. So for two chlorines, the bonding, all right? So if I have chlorine like that, which is Cl, Cl, you have to look at, or if you draw the electron, the electron configuration of chlorine, the valence electron, this is the shared electron, which will now be shared in this overlap. You see here, this explains how the covalent bond is formed. And it is not, or core electron in this case does not participate in the formation of the bond or covalent bond in this case. Sharing of electron is portrayed by the sharing electron. There is an optimum, all right? There is an optimum distance between two atoms where bonding exists. If it is too close, and then if it is too close, the nucleus or the proton in the nucleus will tend to repel, and there will be no bond. If they are far apart, and then there will be no, bond formed. Too far, no bond will be formed. Too close, they will repel. So that optimum distance between the two nuclei such that the bond will be formed is called the bond length, which in this case, hydrogen is 0.4 angstrom. I will get really in details that remember the what? Remember the bond length in this case for hydrogen, but overall is as a result of valence shell bond theory, there is an optimum distance for all molecules such that the bond will exist, which will not require a lot of energy to maintain the atoms together, which will maintain the atoms together. Now, our valence shell electron pair repulsion model does not tell us or does not give us what we call the hybrid orbitals, or how the bond is formed. For example, the connection between, all right, we just assume, for example, here in methane, CH4, just connect that. You can draw the Lewis structure for that. But how does carbon form 4 bonds with 4 hydrogen? If you call, or if I draw the dot structure for, or electron configuration for carbon, 1s, 2s, and then 2p here. 1, 2, 3. Remember, p orbital has, p sub level has 3 orbitals. For hydrogens, 1s, another hydrogen, 1s, maybe I should have this right here, 1s. And then hydrogen here, 1s. What I'm trying to show you here is how do carbon form 4 bonds? 1, 2, 3, 4. 6. Carbon is number 6 on the periodic table, and that is the electron structure, electron configuration for carbon, electron configuration for hydrogen. Each hydrogen has a lone electron for bonding. If you look at the electron configuration for carbon on my whiteboard, it has only 2 electrons, or 2 unpaired electrons available for forming a chemical bond. The question is, how will it now form 4 bonds with the 4 hydrogens? This is now when these terms comes in, hybrid orbitals are generated. That is the mixing of orbitals. You know hybrid, I know you have seen, or you may have hybrid car, right? Electric and gasoline, that is a mixture of 2. Versus fully, EV, electric vehicle, and then there is hybrid. Electric is fully charged, like Tesla is not hybrid. But hybrid means you have gasoline engine and also use electricity. Now, in relation to that, hybrid means mixing. Look at how this will happen. The hybridization now is, what we will do is, we will have to promote this electron. If you look at this, we will take this 1 electron and generate, this will now form by promoting 1 electron to the shell. We end up with 4 unpaired electron, and each electron now will form, each electron will form, or will pair up for each hydrogen, and we use the lone electron in hydrogen to pair up with the hybrid. If you look at this, we have now mixed the 2s and then the 2p here, the 2p. We have used the 2p here to say 1, 2, 3, 1. We call these, we call all of them sp3 hybrid orbitals, hybrid. We have mixed, that means we have all of them. In fact, they are placed 1 to the next, they are placed next to each other. Instead of just having this close, I can just place here that they are degenerate, which means they have same energy, and there are 4 of them, is by promoting one electron so that they are available for bonding. We say this is what? These are hybrid orbitals. So hybridization is the mixing of what? Mixing of atomic orbitals to generate hybrid orbitals for bonding in molecules. There are some cases which also you have to have. There is sp, there is sp2, there is sp3, all right? There is sp2d depending on what you mix. For example, in beryllium, if you look at the electron configuration for beryllium, beryllium is number 4. Beryllium is number 4 on the periodic table, right? So if beryllium is number 4 on the periodic table, orbital filling diagram is, you see this, all electrons are paired up. Suppose it is forming a bond such as beryllium with the 2 fluorine there. How will it now form a chemical bond, yet all electrons are paired up? We do what we call hybridization, which is mixing. So we promote one electron from here, and then you see that we have 2 unpaired electrons, which will now form the chemical bond. sp, you see this sp is now the hybrid orbitals being referred here as sp hybridization, mixing of the 2 electrons, and they will just form an overlap. So for sp3, that means you're gonna mix 3 of the electrons from the p sub level and s sub level. You know what we mean by degenerate? Means they have the same energy. So if we do the hybridization now, from here, these 2 lone electrons will form a chemical bond with each of the fluorine. Remember, from fluorine, electron dot event for what? Electron configuration for this is 1s, 2s, 2p has the sub-level. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There is unpaired electrons here, which will be now form the bond from here. You don't see it here, but the 1 electron in this bond here, and the 1 electron is coming from beryllium. So you do the hybridization. One thing I want you to understand is hybridization is done on the central atom. It is not both or all atoms in the molecule. Forget about the external atoms. We don't do hybridization. Hybridization is done on the central atom so that electrons are available for pairing to form a chemical bond. Remember, we are still on what? We are still on valence bond, out the valence electrons. And to avoid running into a situation where they are all paired up, we do what we call hybridization. sp2 hybridization, there is sp3 hybridization. If you look at this, as I said, we only pay attention to the central atom, sulfur trioxide. Let's see. Give the hybridization for sulfur in sulfur trioxide. In this case, if I do have sulfur, of course, it got to form 3 bonds with 3 oxygen. Sulfur here is 1, we know it's 1s2, 2s, and then 2p here. Sulfur is number 16, all right? Let's see, 3s, I don't know if we're gonna get here, and then 3p here with the 3 orbitals. So we add this, 1, 2, 3, 4, 5. No, we don't pair them up. We don't pair them up. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. Is that what it is? 15. Sulfur is number 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes. 16. So if you look at the sub-level, which is 4S, you know, after 4B is 4S. After 4B is 4S. Now, the last valence bond, the last shell right there, only two electrons are available for pairing them up. So we will promote 1 electron to 4S and we get rid of the shared right there. We hybrid. So here that will go away and the 3 hybrid right here is what we will use in bonding to form the bond sp2 hybridization, sp2 hybridization by promoting 1 electron, and then we mix the 2 to give us the lone pairs, lone electron 1, 2, 3 for bonding with the 3 oxygen, in sulfur trioxide. So remember, if you are not given the element to do the hybridization, always hybridization is done on the central atom. So we're using S and 2 p orbitals, 2p orbitals. I've used methane P4 to show sp4 hybridization. For CH4, you mix 1s and 3 p orbital. The superscript right here indicates how many p orbitals you are using and how many s orbitals you are using, sp3. When you go to something else, let's say sp3d2, it depends on what orbitals you are using. Hypervalent means more than one. This is only hybridization is done on element, or we are limited in this case to only elements on row 2 and above on the central atom. Below row 2, that is row 3 and below, we call those molecules hypervalent, and in this case, we are not going to get into the details of doing that hybridization. We leave that. That summarizes the valence bond theory on how a chemical or how a covalent bond is formed. Now we have molecular orbital bonding theory. All right, molecular orbital bonding theory, which I want us to look at that. Or before we look at that, let's see this if we can get that. Oxygen on O2. So if we have oxygen, that means oxygen is, let's throw the Lewis, the electron, 2p, all right? Oxygen is number 8. So it has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Eight electrons. First structure electron configuration for oxygen. Now, if you look at the fluorine, right? Each fluorine has what? One, this number 9. This is 1s. This is 2s. And 2p is right here. 1, 2, 3. So if I have this 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are looking for hybridization for oxygen. What is available for bonding? The oxygen has how many electrons? It has 8, and from the valence bond we are using the 2p. In this case, the valence shell is 2. There is no way, when we are in shell, it's like we are in what? We are in level 2. Let's say level 1, level 2 in a building or an apartment, level 2, level 1, when we say shell. So what we are using in for oxygen here for bonding is P. All right. Because of the 2s the valence shell, and we are using the we are using the 2p from the lone pairs from each fluorine, because we have 2 of them. They will form a bond with the lone pairs here. That's gonna share. They will pair up to form the chemical in bonding. That's so sp2. You're using 2 of the lone pairs of electron for that oxygen. So to do this, you need to draw the up and down or orbital filling diagram to see the lone pairs of electron, which one you are going to hybridize in order to form the overlap. Now, for double bond, triple bond, there is something I want to show you, and I think you may have used this in describing the bond in one of the labs. You will see a single bond. Let me just explain. Single bond, I know it's a line, right? We call this sigma, because I know we may use this, and we designate that using that, in Greek term. Double bond, which is 2 lines. This is called pi bond. And the pi bond, see here, pi bond and sigma bond. Pi bond, sigma bond. Pi double bond consists of one sigma bond and one pi bond, one pi bond. Whereas triple bond consists of one sigma bond, you know what that means, and two pi bonds, two pi bonds, which are formed as a result of overlap. I know there is a lab which you have to describe the types of bond we have out as double bond, triple bond form. For my hybridization pi bond, there is a pi bond, which is an overlap. You see double bond, seen that before. Triple bond is formed by two pi bonds and one sigma bond, which is the triple bond. We have triple bond, we will include that as well. For the localized electron, you will see that in organic chemistry, I leave that when you do the UV. So that summarizes the molecular, the valence bond theory. How does the valence electron form a covalent bond? There is the molecular theory which explains the formation of a bond. And in molecular theory, from the word molecular, it comes from the word molecule. This is in molecular bonding theory. That means you have an atom here, atomic orbital, and then you have atomic. Where I'm taking you with this is molecular orbital, which will be now what we'll be focusing here to explain how a chemical bond is formed in a molecule, molecular bond. Just like the way we did in the electron configuration of atoms, we will have to use up and down arrow to indicate the electrons. And how are they arranged in the molecular orbitals? This section also will help you in visualizing how you write electron configuration of a molecule. I know we know how to write the electron configuration of an atom. You can also be asked to write electron configuration of a molecule. How are you going to do that? This is memorizing what I do have here, which is the same as when I was saying 1s1, 2s2, and then we have up and down arrow, and then we write that in a similar way. Let me just fast forward to what this stands for, and you should learn how to draw that. Let me just show you that in summary, that you have to say this is atomic orbital, 1s, 1s, and then 2s, and then 2s, and then 2p, and then 2p right here. So if I have 1, 2, 3, 1, 2, 3, we have one right there, we have one right there, one right there. These are atomic orbitals, Remember how we wrote the electron configuration 1s2, 2s2? We are just building it up. Look at how you write molecular orbital. Molecular orbital here, there is a pattern as well. So that we will have to write this, and then that, and then this, that there is a dash there, there is a dash there, and then it's gonna form that. For molecular, like that, you guys should have just have this right here, that is gonna form bond right there. For this, there is 1, there is 1, 2, 1, 2, and then 1 there. So that it's coming from all of them. You have to have that, you have, and then you label this. There is the sigma. You say here, sigma 1s, and then there is the sigma star 1s. There is the sigma 2s, there is the sigma 2s star. The star indicates anti-bonding orbital, anti-bonding orbital. This just the star indicates anti-bonding orbital. If you look at this, because of what I don't have time here, these are the molecular orbitals, and we go with the sigma and pi. These bonding orbitals are constructive, and they are always below. Let me circle the bonding. If you look at this, this is the bonding right here. This is the bonding. The star is under bonding. This is the bonding. This is the bonding. This is the bonding. This is the bonding. These are under bonding. The one I left out in molecular orbitals are under bonding, so that you know where they are. Now, when you write the electron configuration for a molecule such as hydrogen, let's say hydrogen gas, each atom has one. Each atom has one right there. I don't know if I have a different color. I wanted to use a different color. That electrons will occupy the bonding before you put it at the top. You see these bonding orbitals, molecular antibonding orbitals for a molecule. See MO for a molecule. We are now looking at these molecules right here, and we can write its electron configuration as, you know, sigma 1s 1s2. That is the electron configuration for hydrogen gas H2, because the 2 electrons here are occupying the 1s. Look at how we fill in this. You have to memorize. You have to know which one is antibonding orbitals, which one are bonding orbitals for a molecule. Or I've just summarized here that if you have 1s, this is where we have the 1s, the sigma 1s. Let me just blow this up so that you can see the sigma 1s. Sigma star S, the star here stands for antibonding, and electrons occupy what? The bonding before they occupy the antibonding in molecular orbital theory that you all feel in this from the atomic orbitals, and write the electron configuration for that. So this is just the hydrogen atom. What you see here are the molecular orbital, and this is antibonding, and as I say, electrons occupy first the bonding before it goes to the antibonding. Now, if you look at this electron is coming here, each electron is coming here, and remember we are using the valence electrons to write that, or the outermost, or no matter what, you can just use all of them. To be on the safe side, use all the electrons from each atom to form a molecule. So this is hydrogen atom with 1 electron. This is hydrogen atom, and it forms a molecule here. If I was to ask to write the electron configuration, of course, of hydrogen gas H2 is gonna be sigma 1s2, all right, which means we have 2 electrons in 1s. Now there's what we call the bond order, which you will be calculating, all right. Bond order is number of, look at the equation for bond order, number of what? Bonding electrons minus number of antibonding electron in the outer. Once you have this electron configuration for a molecule, number of bonding electrons, how many bonding electrons do we have? We have 2. How many non-bonding electrons? That means electron occupying here. We have none. That is why you see 0 here. We have 2 electrons here, 2 minus, and then it's gonna form bond. This tells us how many bonds the molecule can form. If the bond order is 0, that means that molecule will not exist. That molecule will not exist. So how will I calculate the bond order? It is the total number of bonding electrons minus the total number of antibonding electrons, and then you divide by 2. If this is 0, that means that molecule will not exist. As you end up with more atom like this, bond order of 0 does not exist. Therefore, helium H2 does not exist, because in helium we have 2 electrons. We have 2 electrons, 2 here and 2 here. So 2 minus 2, bond order of 0 means does not exist. So unless I know how to generate this diagram for molecular orbital from atomic orbital, you will be able to answer this question on bond order. I have minus, I know bonding minus and the bonding. This is bonding minus and the bonding is 0, means no exist. Maybe when we get to, other molecules, you will see how the orbitals are generated. Right here, all right, this is the summary of, how to write the electron configuration of a molecule. The number of molecular orbitals formed equals to the number of atomic orbitals. Yes, the same, it's just gonna play out. Each molecular orbitals can accommodate most 2 electrons. Yes, that's what we saw. That's why we have 2 electrons. When molecular orbitals have the same, they are populated 1 electron under each orbital, same spin. Yes, so it's gonna be like, same spin, they will singly occupy 1 electron. We will see that in determining what we call the diamagnetic, paramagnetic. Using lithium, see if we have L2, this is, assuming that we have lithium L2, we can, all right, write the electron configuration for each lithium. And for a molecule such as for this now, L2, these 2 electrons will, the 2 will occupy the bonding, will occupy the non-bonding. And if you look at this, 1 electron is coming from each. If you are to write electron configuration for Li2, it is sigma 1s2, sigma star 1s2, and then sigma s2, because we have 2 electrons, and then so forth and so forth. That's how you will write electron configuration for that. This is molecular orbital diagram for this molecule. I know you can reproduce this. If you cannot, you need to learn right now. How do you continue beyond this? This is how it looked like. This is what I want you to learn. I know I used before that the 2p, you'll do the same thing for the 3s. What is missing here is the 1s, because it's just going to cancel out. There is the 1s below, depending on which molecule you will be dealing with. So for molecular orbital diagram for elements on the p block, the 2p here, look at the bonding and unbonding. If you look at the bonding and unbonding, our focus is right here, because this is what we'll be looking at in filling the electrons. So if I was to fill this molecular orbital with electron, it depends on what I have here, and it depends on what I have here. And I'll start by pairing electrons here. I'll start by singly occupying this and then start pairing them up before I singly occupy this, and then I'll go up there. That's how you fill the molecular orbitals with electrons, depending on what molecule we are dealing. This molecular orbital will be used in another concept of paramagnetic and diamagnetic. What I mean by that is a molecule which will be attracted in the magnetic field, a molecule which is attracted to a magnet, for example, is paramagnetic. Diamagnetic will not have magnetic properties. Paramagnetic, that means it will have a magnet. Why am I bringing up this? Is because this molecular orbital will help you in answering that question. So if all electrons in the molecule are paired up, and then it is diamagnetic. If there is a single unpaired electron in the molecule, once we do that, then we say that the molecule is paramagnetic. Here is an example. If I look at these are paired up. If there is unpaired, say paramagnetic. If you look at neon, this is group A. We know group A, they do not exist as molecules, they exist as atoms. We only have neon gas as an atom, but it cannot exist as Ne2. That's why we have a bond order of 0. Bond order of 1, it means a half. This is bonding minus antibonding. We don't have antibonding, so a half of 2 is 1. If you look at this, 4 minus 0 is 4. Half of 4 is 2. That's what we have here. But here is 6. I don't see antibonding up there. That's why we have what? 3 and so forth. That's how you look at the bond order. I mentioned paramagnetic and diamagnetic, and you are wondering, how did I end up with that? These are molecular orbital. And why do we say this is paramagnetic? It has unpaired electrons. So if I don't do well in drawing the molecular orbital diagram for a molecule, in order to see that I see that they are unpaired electrons, there is no way you will say that this molecule is paramagnetic. So paramagnetic means in the molecular orbital diagram for that molecule, we have unpaired electrons. If all of them are paired up, we say diamagnetic. All these are diamagnetic because if you look at this, paramagnetic because we have unpaired electrons. If I look at this, diamagnetic, all of them are. This one, of course, dash because the molecule does not exist. If it does not exist, how will they have analyzed and put it in the magnetic field to see if it is magnetic or magnetic? That's how you can look at paramagnetic or diamagnetic. There is a diagram in the text which oxygen is passed. All right. There is a diagram in the text where oxygen gas is passed through a magnetic field and it is attracted towards the poles of the magnet because it is paramagnetic. Let's see. The highest energy, the highest occupied molecular orbital, MO in fluorine. Fluorine is what? So if I do that, all right, let's see. I'm gonna skip this and see how we can have that. All right. Fluorine has 9 electrons. Let's just use this. I'm just going to use this. So 1, 2, 3, 4, 5, 6, 7, 8, 1s, 2s. Oh yeah, I missed something. That's why I was saying that what is going on. I didn't pair. So I didn't pair this 1, 2, 3. Remember, each fluorine has 9 electrons. So atomic or electron configuration for the first fluorine here is this 1s2, and then I pair this 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. You see that? And then the same here, 2, 3, 4, 5, 6, 7, 8, 9. So if I'm to, if I'm to pair them up, this will cancel out. Sometimes we don't, this will cancel out. If we put here, here, and the bonding, assume that this will disappear. This will cancel out. But now the outermost 2p, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the electrons should come on these molecular orbitals. So if I have 10, I have 2 here. 1, 2, 3, 4, 5, 6, all right, 7, 8, 9, 10. Remember, we should have 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The question is, you need to know what is the highest. You need to know how to label this. This is 2 pi based on what we have here. Blow it up so that you can see. Fluorine. This you see here is what we have here. So I see the highest here is 2 pi p. If you don't know how to name them, all this, you got to learn right now. That how do I have this is, there is 1s, there is sigma 1s, there is sigma star 1s2, and 2s2 is because of the 2 electron. 2s2 is because of the 2. 2p2 because of what we have. 2p4 because we have 4 electrons in the bind. So the highest for this is pi star 2p orbitals. Pi star 2p orbitals, which answers this question. The correct answer is pi star 2p orbitals. It's not something you memorize. You really have to draw the molecular orbital diagram. It is with practice that you will nail down how the order is occupied. This is the order in which electrons are occupied in molecular orbital. These are molecular orbital diagram. In electron configuration for atoms, we just say 1s, 2s, and then we put the arrows as we count the number of electrons. But this is a slightly different approach, even though it is the same thing. So long as I can know the order in which the energy, this is according to increase in energy. This is the highest in energy, this followed by this, followed by this. This has the lowest, this has the highest, and this is the order in which. I don't think we will copy on this so long as we have learned the concept. I'll not get into the D or stuff like that. We'll only have to go up to the P orbitals. What is the bond order for this? So let me just minimize this. We are looking at the bond order for nitrogen. We cannot memorize this, all right? We cannot memorize this. What we will do is write electron configuration for nitrogen. Nitrogen is number 7. So we have 7 electrons. So if I have 1s, 2s, and then what? 2b. 1, 2, 3. I'll do the same thing for 1s. So I have here, and then 2p, and 2s, and then 2p here. 1, 2, 3. So for each nitrogen, this is atomic orbital. Atomic orbital. This is atomic orbital. There is the 1s. You see that? I should have used this right here. That what is coming from each one of them here will form something like that. And then here will form something like this. Now for this, it will form this, it will form 1, 1, it's gonna form 1, 1, and then there is a dash right there. So that when we fill the electron now for number 7, 1, 2, 3, 4, 5, 6, 7. And then here is 1, 2, 3, 4, 5, 6, 7. I'm writing, drawing an orbital electron configuration for orbital diagram electron configuration for each nitrogen. So nitrogen on this side, nitrogen on that side. Now, molecular orbital, because that is when we will now use the equation, a half of the bonding minus antibonding. There is no way we will know how many bonding electrons do we have, all right? These will have 2, these are bonding, these are antibonding. It's gonna cancel out, we don't need this. These will cancel, this will cancel, that will cancel, that will cancel, this will go away. Now, the point of interest is once we cancel that, the 2p is our focus now, that we need 3 to account for 6 electrons. So I'm just gonna have 1, 2, 3, 4, all right, 5, 6. Remember, this is these are antibonding. These are antibonding with the star. The one I put a star. And what we say is a half bond order. A half bonding electrons minus anti-bonding electrons. So a half of, in this case, we have 6, all right? 6 minus 0. I don't see anything in the star. You have to account for the 1 star. The stars are on the bonding. We don't have any electron in the bonding. So if I do this, this is 3, which means nitrogen form 3 bonds, triple bond. And of course, from the Lewis structure we saw last time that nitrogen has 3 bonds, and the bond order also tells us that. So this is what you need to know, that how do I feel the electron? Forget about what we have here. The outermost here is what we are focusing on. And you need to remember, all right, that for nitrogen, this is what we had, all right? This is what we had actually, molecular orbital for nitrogen. This will cancel out. We don't see the 1s, but when you look at this, this is what we are focusing on. These are the bonding, 6 electrons. I don't see any antibonding. The star is antibonding right here, minus 0, bond order of 3. Just to, give you an idea on how to go about with that, I'll ask you the paramagnetic. This is a question of molecular bonding. Diamagnetic also, it has to do with the molecular bonding. The bond order also will be on the concept of molecular bonding, all right? All right, I've explained that what is meant by diamagnetic. Diamagnetic means it cannot be attracted towards the magnetic field. They are weakly repelled, so magnetic field. But paramagnetic, they are magnetic, put it that way. Because of unpaired what? Unpaired electrons. Unpaired electrons. That's all what I want you to know. You can try that on your own and see how you get. This is an illustration of what is meant by paramagnetic. If you look at the oxygen being paramagnetic, these are magnet, these are magnet. Somebody is pouring liquid nitrogen, liquid oxygen, and they get stuck here. I don't see it going through because of the magnetic field, This is just the same thing for nuclear. The hetero means different atoms. Still, we use molecular orbitals, nitrogen and oxygen. Say heterogeneous, meaning they have the same, they have different atoms. This is nitrogen atom, this is oxygen. We still use the same molecular orbital diagram to write the electron configuration. If I look at the lone pair here, or lone electron, sorry, is diamagnetic. That's all what I want to cover in chapter 9. I'll look at the questions and post a quiz for chapter 9. We will meet again next Tuesday. I do have chapter 10 PowerPoint slides available. Please read on that. We have 1 week, all right, and I will make, all right, listen, I will make the study guide, the material for final exam available by tomorrow, because you can't get started, that you need to know this. Remember, final comprehensive exam will cover up to chapter 10. I'll cover chapter 10. We'll see how far we go on Tuesday. All right, it is relatively easy chapter. We have covered this before. The gases, all right. The calculation in chapter 10, they are not so hard. It's pretty straightforward. Other than that, please kindly do the survey of the course. It will really help me. I don't see what you write. You know, we are approaching the end of the semester, and always it's a survey of the course. I think should have been available either last week, or it will be available this week, and it will be available even next week. I'll see you again next time, Tuesday. Thank you for tuning in this morning. The class is dismissed. Have a wonderful afternoon.
Can I ask a quick question before you leave?
Yes, thank you.
Okay, just for that last learning check, just because it looks like that they're ions, do you just treat them the exact same way, like you would just take off the 2 electrons?
Yes, you'll take the 2 electrons.
Like, yeah, okay, would you mind just saying like what the answer is, just so that whenever I work it out, I can just like know right away if I have it right or wrong?
Yeah, let me just, for all I know, there was some previous assignment or learning check also, I didn't do that. I will share the answer for that and how you arrive at that, so that instead of saying doing this, you have just to compare. Can you work on that and I'll share with you?
Absolutely, thank you.
So that, you know, you don't, if you look at it, you may say, how did, you know, and then you get stuck, I better solve it, and then send it to you, you compare just with your answer, okay?
Okay, thank you.
All right. Any other question? If there's no question, and then I'll see you again next week. Thank you.